start by going over how to solve exponential equations. If you have an exponential equation, so exponents are a part of the equation that you're solving, the first thing to do is to see if you can have the bases match, especially if there are exponents on both sides of the equal sign. If the bases match, like with 3 to the power of x and 3 to the power of 5, they both have a base of 3, then we can just set the exponents equal to each other and solve for x. In this case, x would be 5. In the second example, the bases match again. We have a base of e and a base of e. Because the bases match, we can just set the exponents equal to each other and solve for x. And x would equal 1. In the third example, the bases do not match. We have a base of 6 and a base of 36. But we can get a common base by rewriting 36 as 6 squared. 36 is the same thing as 6 squared. So we have 6 to the power of 2x minus 6 equals 6 squared. And then we also have 3x minus 5 up there in the exponent. Now that the bases do match, we have two bases, both of them 6. We can set the exponents equal to each other. 2x minus 6 equals 2 times 3x minus 5. And solving this equation, we get that x equals 1 again. Let's try a couple more of those. In this next example, the bases do not match. We have a base of 100 and a base of 1/10. But we can get a common base by using 10 as our common base, because 100 can be rewritten as 10 squared, and 1/10 can be rewritten as 10 to the power of negative 1. But we got to keep these exponents on. So this one had an exponent of x, and 1/10 had an exponent of x minus 3. But now that the bases match, we have base of 10, base of 10, we can set the exponents equal to each other. 2x equals negative 1x plus 3, which means x equals 1 again. In this next example, again, the bases do not match, but we can get a common base. And so that's what we're going to do. 9 can be rewritten as 3 squared. 27 can be rewritten as 3 to the third power. Keep the original exponents up there. And so now that the bases match, we set the exponents equal to each other. 2 times 2x is 4x. 3 times x minus 1 is 3x minus 3. And we get x equals negative 3. Now, what happens if we can't get a common base? So this next example, we have a base of 2 and a base of 7 on the other side. And 7 doesn't have an exponent, but it's still a base. There's an invisible exponent of 1 there. But we can't get a common base between the two. So whenever you're trying to get rid of a base, we've got an exponential expression right here. Whenever you're trying to get rid of a base, you're going to take the log of both sides, because logarithmic expressions and exponential expressions are inverses of each other. And so to get rid of a base of 2, we're going to take the log base 2 of both sides. So just like addition and subtraction undo each other, multiplication and division undo each other, logarithmic expressions undo exponential expressions. So the log base 2 cancels out with that base of 2, and all that's left on the left side of the equal sign is x. On the right side of the equal sign, we have log base 2 of 7. Now you can't type that into your calculator, so we have to use the change of base formula, which says log base 2 of 7 is the same thing as log of 7 divided by log of 2, using that common log. When we divide, we get approximately 2.807. And remember, what we were trying to find, we were trying to figure out what exponent to put on 2 to get 7. And so make sure your answer makes sense. We know that our answer is going to be less than 3 because 2 to the third power is 8. And we want our answer to be 7. So our answer is less than 3. 2.807 seems reasonable. On the next example, again, our goal is to solve for x. But to solve for x, first we need to get rid of this base of 7, and we can't get a common base on both sides of the equal sign. So because we can't get a common base, we need to get rid of that base of 7 by taking the log base 7 of both sides of the equal sign. So on the left side, the log base 7 cancels out with the base of 7, and we're left with 9x. On the right side, we have log base 7 of 15, which you cannot type into your calculator. So we use the change of base formula, log of 15 divided by log of 7. And when we do that, we get 1.392. And then we still don't have the x by itself. We need to get rid of that x by dividing by 9 on both sides. X is approximately 0.155. Here's another example, but just a little bit spicier. Our goal is to get x by itself. We're not going to do a log right away here because there are some numbers we can get rid of right away. We're going to get rid of all these third wheels first. And we can get rid of that minus 7 easily by adding 7 to both sides. So try to isolate your exponential expression as much as you can first. We can divide both sides by 4 now to isolate a little bit more. But at this point, we get a little bit stuck because the next thing we need to get rid of is the e, and that's the base. So to get rid of a base e, we need to take the log base e of both sides, and the log base e is the same thing as ln. So we're going to take the ln of both sides, and when we do that, the ln and the e cancel each other out. ln of 5, you can use your calculator to get approximately 1.609. And then lastly, we need to divide by negative 0.3 to get about negative 5.365. We're going to switch gears now and talk about how to solve equations that have logs in them. So logs and exponential expressions are inverses of each other. So whenever we're trying to get rid of a log, the inverse of that is by creating an exponential expression. In this case, we're trying to get rid of log base 5. So to do that, we're going to use an exponential expression that has a base of 5. And whatever you do to one side of the equation, you do to the other. So what we're actually doing, we're creating a base of 5. So how we would read the left side of the equal sign is 5 to the power of log base 5 of 4x minus 7. It looks a little funky, but basically that base of 5 cancels out with the log base of 5, and we're left with 4x minus 7. And on the right side of the equal sign, the 5 cancels out with the log base 5 again, and we have x plus 5. So because both sides of the equal sign had a log base 5, basically those two cancel each other out. And so we have 4x minus 7 equals x plus 5. 3x equals 12, which means that x equals 4. It won't always be quite that simple, though. On this next example, there's not a log base 4 on both sides of the equal sign, only on the left side. So to get rid of that log base 4, we're going to create a base of 4. And if we do that to the left side of the equal sign, we also need to do that to the right side of the equal sign. So when we create a base of 4 on the left side, the 4 and the log base 4 cancel each other out, and we have 5x minus 1. On the right side of the equal sign, it did not cancel out, so we have 4 to the third power, or 64. So when I continue to solve this for x, we end up getting that x equals 13. The next example also has a log, but we're not quite ready to get rid of that log yet because we can isolate it first by dividing both sides by 3. If you can isolate first, isolate as much as you can first. Now we need to work to get rid of that log, and that log is the natural log, which means it has a base of e, which means to undo it, we need an exponential expression that has the base of e. So the e, the base of e, cancels out with the log base of e, or the ln. And so we get that x equals e to the 8th power, or if you want an approximate answer, e to the 8th power is approximately 22,980.958. One more example, and this last one is a little trickier because there are 2 logs on the left side of the equal sign. So what we need to do is use properties of logs in order to take those 2 logs and condense it into 1 log. So the properties of log says that if you have addition, that's the product property. So I can multiply 2x times x minus 5 when condensing those 2 logs into 1 log, or 2x squared minus 10x. Now we're going to solve this just like we did the others. We need to get rid of that log, and it doesn't have a base on it. When there's no base on the log, there's an invisible 10 there. So we're going to use a base of 10 on both sides, so that the 10 can cancel out with the log base 10, the common log there. And we have 2x squared minus 10x equals 10 squared, or 100. Well, now we have a quadratic equation, and to solve a quadratic equation, we need to make sure that the equation equals 0 first. So I'm going to subtract the 100 from both sides of the equal sign to make it equal 0. And there are 2 ways we can solve this. Well, actually there are multiple ways you can solve this. My 2 favorite ways are by factoring or by using the quadratic formula. If I'm going to factor this, which is my favorite way of solving if it's factorable, the first thing I'm going to do is divide both sides of the equation by 2. Because all of these numbers divide evenly by 2, it makes it a simpler quadratic to factor. Now I'm going to factor this new trinomial. The 2 numbers that multiply to negative 50 and add to negative 5 are negative 10 and positive 5, which means if those are my 2 factors, my 2 solutions are x equals 10 and x equals negative 5. But before you get too excited, we're still not quite done because log equations can give us extraneous solutions, which means you did all of the work right, but when you go to plug in your answers, it doesn't work. You'll know you have an extraneous solution for logs if when you plug in a number like negative 5, if I plug in a negative 5 over here, I get log of 2 times negative 5, which is negative 10. And you cannot take the log of a negative number, which means because negative 5 gave us a negative 10, negative 5 is an extraneous solution. But when I plug in 10 over here, I get log of 20. And when I plug in 10 to the other one, I get log of 5. You can take the log of both of those numbers, so 10 is a solution. but -5 was not.